Thank you. I did it eventually, but it was very helpful. I mean, the right information.
All right, hi everyone. It's a pleasure for me to introduce Dr. Sibasish Laha today. Sibasish obtained his PhD in astrophysics in 2014. He joined the University of California, San Diego as a postdoc, and then in 2019 joined NASA Goddard and University of Maryland in Baltimore County. And he's one of the lead team members of SWIFT, a NASA mission. He extensively worked on AGN X-ray astrophysics, and in 2022 he was awarded the NASA Exceptional Scientific Achievement Medal. And today he's going to talk about activities at the center of active galaxies. Please take it away.
Thanks, Fabio. Can everyone hear me? And in the Zoom here.
Yeah.
Perfect. So, as Fabio mentioned, I am an observational astrophysicist in X-rays, and I study active galaxies, different types of phenomena at the centers of active galaxies. So, my talk today will be focused on three aspects of active galaxies. One is the feedback, which is an important element of black hole galaxy coevolution. The second point would be the distribution of matter near the black holes, the supermassive black holes. And the third would be the changing location, which made news very recently, which changed accretion states and flared up. So to begin with, most of you are aware of the bigger astrophysical questions about this cooling flow problem in the intercluster medium, where the interclusters medium should have cooled quite fast given the cooling rates, but it's not getting cooled because something is heating it up. And also, like, visible to baryonic mass ratio is incompatible between the theory and observations. Theory predicts more, and we don't see as much variance. And the most important relation, the M sigma relation, which actually catapulted the relationship between the supermassive black holes at the center of galaxies and the galaxy as a whole to co-evolve in cosmic time, is not yet very clearly understood. And early theories by Silicon Rees and King et al., and later on by Hopkins and Elvis have pointed out that feedback is a very important problem. The black holes, while accreting matter, also gives feedback. So this feedback in the form of outflows, which interacts with the host galaxy, actually is a very important, forms a very important relationship between the black holes and the galaxy. So today I'll talk about some observational evidences of such feedback. And I'm sure, like, to an audience which has expert theorists, I would also get some glimpse about the theoretical advancements done on these fields. So this is a big field, and I'll try to be as compact and as compact as possible, but I won't be able to do justice to this entire field because it's like the whole entire talk in itself. So so again, like most of you understand what is the central engine of an AGN, and the most important components that we study are the supermassive black hole, the accretion disk, the corona, and the wings, and sometimes nascent jets in case of radio-loud AGN. And the radio-loud AGNs form a very tiny fraction, like around 10% of the known AGN population. And we still don't understand clearly how these jets are formed, how corona is being heated. Corona is an X-ray emitting, predominantly X-ray emitting plasma, which sits right near the black hole around 10 gravitational radii. And it depends on the luminosity of the corona depends on the accretion rates of the black holes. And these have a very nice symbiotic relations, both on the accretion, from the accretion disk point of view, also the torus. Torus is something which which we think that it's a toroidal structure around the entire supermassive black hole and the accretion disk, which is gravitationally sustained and which possibly feeds the black hole. So what I'll be talking today about is these outflows, the feedback that happens through winds, mostly winds. I'll not be talking about jets. I'll be talking about radio-quiet AGN, the winds in the radio-quiet AGN, and how possibly the torus feeds the black hole, and the changing look AGN, which changes the state of the accretion. The rate of change of accretion is very rapid in human timescales. It just goes from one state to another. Just to give you a glimpse of how AGN astrophysics define the types of galaxies. The type 1 galaxy is something which we see face on. That is, we can see the supermassive, we can see the black hole and the accretion disk and the broadline region. And for type 2 galaxies, which we think is obscured by a very thick torus, which is a neutral and dusty cloud, gravitationally bound around the black hole system. And if our line of sight is through this torus, then we can't see the, we can't see this central engine. So what we see is just some narrow emission lines around this, and we don't see the accretion, main accretion phenomena. Some of the open questions in active galaxies are, what is the exact geometry of the central engine? How does the black hole accrete matter? How does the matter from large distances lose angular momentum and fall into the accretion disk? I know Professor Naran has worked for many years on these problems, and we have observational evidence of matter very near to the black holes. And how are these powerful outflows generated from AGN? So how accretion disk and other aspects of the SMBH system generates these outflows. And these outflows are very, very powerful in terms of its kinetic luminosity, its momentum transfer, and these outflows are generated very near to the black holes. And how these outflows couple with the host galaxy. This is very important because if you consider feedback from the whole black hole system, you need to understand how these outflows are coupling with the host galaxy gas and dust. And this coupling is not very straightforward because you have to understand the dust composition, to understand the momentum and energy conservation rates, and there are many aspects to this. So these are open questions, and today we will take a tour from the observational point of view, especially the X-ray observational point of view. And highly energetic outflows are actually supported by theories as well. Like we not only need them, they are a byproduct of this entire supermassive black hole and accretion theory. So there has been a lot of feedback models in the last 2.5 decades. In particular, I should highlight Hopkins and Elvis in 2009. They suggested that it could be as low as 0.5% of the bolometric luminosity is enough to give feedback to those galaxies. And that is something very interesting because in some of the outflows, we do see this limit is crossed, and we think that this could be a reason. I mean, defining the MC-Burr relation between the supermassive black hole and the host galaxy bulge stellar velocity distribution.
So the specific feedback you're interested in here is what part of the energy of the outflow gets dumped back into the accretion disk?
Exactly. Accretion disk and also the host galaxy itself. Exactly. So, so I'll be briefly mentioning, I'm again reiterating briefly in the sense that there is a huge amount of work being done, and I'll be highlighting only a few of them, and I'll be interested to talk to you more if you want to know more about the ionized outflows and molecular outflows. I mostly worked on the X-ray band of these outflows, and And these two types of outflows are major contributors to not only just the energy dumping, but also momentum dumping and matter dumping into the host galaxies. And okay, the feedback that I'm talking of is actually to quench the AGN phenomena itself. So there has been theoretical studies predicting that the AGN phenomena are like black hole starts accreting and it accretes at a very high rate, gives feedback, removes the gas. So that's the feedback, and then it quenches. And then again, the angular momentum transfer takes place, and again it feeds. So it's an intermittent start and stop phenomena in the AGN. So Milky Way, for example, had been an AGN long time back. So in the last few decades, we have seen quite a few, very energetic outflows coming up from the black holes, black hole vicinities. So first is the broad absorption lines that we see in the ultraviolet. They're around like 10 to 20% of AGN showing the broad absorption lines, and they are seen in the UV. HST has done a huge amount of work on that. And then comes the warm absorbers. Warm absorbers are ionized absorbers in the soft X-rays, detected in the soft X-ray, the wavelength band of around 4 to 30 angstroms. And these warm absorbers are from the ionic states of oxygen, carbon, nitrogen, and they have substantial amount of energy and as well as momentum outflows. And the last but not the least, this is the UFO. This is the ultra fast outflows, not the unidentified flying objects. I wish it could have been the unidentified flying objects, but unfortunately, we as scientists, we can't make fun of things. But so UFOs are ultra fast outflows. Why they're ultra fast? Because you see, like these outflows are mostly of the order of so this is so I later Astronomy review in 2021, the picture from there. Ultra fast outflows are really interesting because they are very nearby. If you assume the virial radius, and the velocity is almost like a fraction of the velocity of light. And these ionized outflows, since they're super ionized, you just see the iron band absorption. So you see this narrow iron band absorption. These are super ionized. All the electrons are just moved away from iron. So iron, these are mostly detected in the 6 to 7 keV energy band. And the worm absorbers are something which is of like lower velocity and lower ionization state, but it has a higher, huge column density. But the interesting thing is that they carry a lot of mass. They carry a lot of energy because of like velocity squared gives you a huge amount of energy, but their velocity is smaller, but they carry a huge amount of mass because of the lower ionization parameter and the lower energy. The other absorption lines I would not talk about is the broad absorption lines, which is a very interesting field of work, and they have they are also important feedback agents, and they come very near to the black hole. So maybe the narrow absorption line, for example, comes from very far away. So maybe it can be that these systems are not isolated. These are all multi-phase outflows. The UFO charging on the outer accretion disk to produce the broad absorption lines giving the warm absorbers then giving the narrow absorption lines, and finally depositing energy and matter in the host galaxy. But the interesting thing is that the percentage of occurrence differs a lot. For example, UFOs are around 40% in local AGN. Worm absorbers are around 70%. Broad absorption lines are found around 10 to 20%, and narrow absorption lines are more than like around 40 to 50%. So the occurrence is not uniform. So this multi-phase concept is good, but it's not yet robustly identified. So what do I mean by worm absorbers? So it's like from an observational point of view, you see a mess of absorption lines, And how to make things out of it, we use codes. We use simulation codes like cloudy, for example, you need 3 layers of absorptions. So it means that there are 3 layers of clouds along the line of sight to the galaxy. And when you combine these 3, you should get this. So this is a fitting done for a source, which is MCC 63015, which is a very famous worm absorbed source. And if you plot the ionization parameter and the NH, so NH is the column density. So its column density means if you have a cylinder, a 1 centimeter square surface area along the line of sight, and if there is a long along the line of sight some distance L, then you just collapse that so that you know the number of particles in that particular 2-dimensional cross section. So that's how we calculate the log NH, so the number of particles that you're seeing along the line of sight.
That's a conclusion from simulations that you can divide it into 3.
Exactly. So, and this is how we obtain our results, and we characterize these absorption lines. We measure the energy, we measure the momentum and everything. I'll come back to this later. Let me first give a glimpse of how we do this fitting. It's very complex because we have the continuum from the agent. The agent continuum contributes a big UV bump, which comes from the action disk. The power comes from the corona. Soft X's comes from something which we don't understand yet. But this is the portion where the worm absorber sits, so we have to model them properly. So it comes, so the XMM epic PN observation is kind of a broad band, like 0.3 to 10 keV, and we use this along with the UV bump to model what you call the worm absorbers in the RTS. So these are iterative modeling, and we find that this type of modeling is very important. So we have to feed in the simulations with this SED to understand how much ionized a cloud can be, and those clouds are absorbing around a line of sight. So the measurements of Xi, NH, and the speed of the clouds are obtained through pretty iterative simulations. Some other type of obscurations. So, for example, this is a different type of absorption. This is an obscuration event, where a cloud comes across the line of sight and passes across the line of sight. And this happens to different sources at different time scales. And time domain science has actually enabled us to detect more of these events. So this was the first of its kind in NGC 45548. And we now have at least like 10 sources such that with these type of things. So you see the spectrum was nice and fine. Suddenly in 2013, it got absorbed, and it stayed absorbed for like 7-8 years, and then it's gradually getting out. So it means that the cloud, which is quite near to maybe a parsec scale cloud, which is very near to the supermassive black hole, passing across the line of sight. And these type of obscuring outflows, or you may say the obscuring clouds are very unique, and we still don't understand. Maybe it's a BLR outburst, like the broad emission line just burst out because of some radiation. We don't understand. Another type of thing is the UFO. That's just mentioned. The UFO, you see an absorption line in the iron, and this is highly blue shifted. So it should be somewhere here, and it's blue shifted. And from the blue shift of the line, you know that the speed is around point something c. So, and the P sigma profile helps you because the emission and the absorption, if you model, then you can understand the amount of matter in the line of sight.
What are the brown rhomboids in the left-hand graph?
Oh, this is the hard X-ray observations. So hard X-rays are not absorbed by clouds because you don't have much of atomic transitions happening beyond 10 keV.
No, but what are the little diamonds represent?
Diamonds represent the data from integral. Integral is a telescope, and the diamonds are the hard X-ray data from the integral. And these are like New Star is a hard X-ray telescope which extends to a little bit of like 3 keV. But Chandra and XMM are perfect examples because they extend to the soft X-rays, and this is where this absorption takes place.
So these are not narrow line clouds or broad line clouds or something else?
This is something else. This is something else in the sense that the UV counterparts, if you see, you can actually distinguish between the absorption lines, and they are not very fast outflowing, so they're not broad absorption line clouds, not BAL clouds. And they have quite a high column density, higher than the worm absorbers, so they're not worm absorbers. So this is a different class of object, different class of clouds. And this is a more recent example of this. I mean, you can see that there has been an obscuration, like it was just sitting like this here. In the gray ones is like 2009, it was just sitting like that. In 2021, in 2020, it showed a dip, and then again it's coming up. In 2021, it's coming up. So these type of clouds which are moving across the line of sight is something very interesting, because now the time domain science have really taken the lead. We can actually know in real time, because a lot of all sky surveys are there. We can know in real time when the hardness ratio changes. Hardness ratio is the ratio, sorry. Hardness ratio is the ratio between the hard divided by the soft. So hard is usually unabsorbed because you don't have much of atomic transitions here. So this part is mostly unabsorbed, and you have a nice handle of the continuum from the agent directly. If the soft changes up and down, you can say that, okay, obscuration is happening, just focus all our telescopes there and let's see what's happening. And so that's a type of phenomena that we are like going through a lot nowadays more, and a lot more nowadays, and we're trying to understand what's going on. Another type of outflows that I should say is important is the soft X-ray UFOs. Now I've been talking of the UFOs in the hard X-rays, like 7 keV or so. Now the soft UFOs, the band where we have worm absorbers, we actually have absorption lines which are very highly blue shifted, means very high speed. And this actually opened up a nice thing that we think that these are like clouds which are like embedded within each other, like the UFOs and the worm absorbers are embedded within each other. So these are the typical ionized outflows that we deal with, and I must say that most AGN has something or the other. So talking of the properties of these outflows, again, it is a very short description. There are lots of other discussions, a lot of other properties. One thing we should ask ourselves, what is the launch radius of this particular outflows? Where does it launch? So for launch radius, we can use a virial, if you know the black hole mass, we can use the virial relation to understand things. And worm absorbers are typically like launched around in the dusty column density, where like the torus is there and the outer accretion disk. And UFOs are launched very near to this. But another thing very important, I should tell you, it's our limitation is that we don't have a good handle on the distance of the absorbers, because if something is along the line of sight absorbing, it can be anywhere along the line of sight, unless you have a good handle on where it is sitting through indirect means. Absorption spectroscopy does not give you distance, covering factor, or the filling factor. What you see is a collapsed version of anything that is happening in the 3 dimension in a 2 dimension. So that's a big issue. And when you say that, can these gas outflows give feedback? Answer is yes, and answer is we don't know. So yes, if we correctly understand the distance and covering factor, it can be orders of magnitude different. But Arcus, for example, missions like Arcus, Randall Smith is the PI proposed mission, and these type of missions in future can actually get hold of these factors.
How you said they'll get a hold of it maybe indirectly. Can you say something about
Yeah,
that?
sure. So the thing is, for distance, you have to know either you have to know the variability timescales, like when a continuum is varying, how it is responding, you know, the recombination timescales, and from there you can get the distance, because you know the density. For density, you need the density sensitive absorption lines. So I can talk about that later. But density absorption, sensitive absorption lines, you need to have a very high resolution, spectral resolution. You have to measure each absorption line, especially the metastable lines, and get the density. And if you get the density of that cloud and you know how it is responding with respect to the continuum, you can definitely get a very good handle on distance. And this has been done from many sources. Unfortunately, you need hundreds of kiloseconds of Chandra time, for example, or XMM time. And that is challenging because if you write a proposal and ask, I want 500 kiloseconds to do this, the panel will say, come on, we can do like 10 other science cases. Why should I give you 500 to get the density? And that's the reason why we are proposing Arcus. Arcus would have enormous amount of effective area and spatial resolution. I'll show you a figure with that. So we need these missions. And if we have these missions, we know the density, we can see the distance, and for the first time, we can actually, in a bigger sample, we can know how much feedback, not just the energy feedback, it's also the matter amount of matter that is being deposited in the host galaxy. We can measure all of these. I'll give an example. So so these are my papers that I've published quite a few years back. To give you an estimate, if you plot the amount of luminosity absorbed in these areas where it is very deep, for a sample of sources, and if you calculate the mass outflow rate, you see some trend that the mass outflow rate increases with the luminosity absorbed. So amount of matter that is being deposited from for these clouds on the host galaxy is higher for higher absorbed systems. So it's obvious to us, but but we have quantified something like this. And this is interesting because apart from energy deposits, we have matter to be deposited in the host galaxy. Now, in terms of feedback, I told that worm absorbers are a little dicey, but for UFOs, I think it can give energy feedback. And this shows a plot of the bolometric luminosity versus the kinetic luminosity. Kinetic luminosity is standardly calculated with, so for UFOs, we have a distance of measurement for virial radii, which is a very hand waving, but we expect them to be very near because it's very high in gas. And definitely UFOs can give, and that's why CRISM is launched. So CRISM has been launched last year. So CRISM is a telescope which is a high resolution, high effective area calorimeter, and which was launched last year. And the data are not yet public, so I can't show you anything, unfortunately. But it's like a successor of Hitomi as telescope, which unfortunately died in space. We could see very narrow emission lines and absorption lines in our X-rays. So yes, UFOs can give, but the thing is, our worm absorbers in UFOs is just the same type of outflows, just impinging somewhere in the ISM and creating the worm absorbers. The answer is we still don't understand. Yes.
I have a question. That last red point, that's a 10 to the 48 ergs per second.
Yeah, so
Is there a wind luminosity that high?
yeah, so also the error bars are large.
Okay, so I should just ignore that and look at the bottom?
Yeah, so thanks for pointing. But the thing is, like, in these cases, what happens is like the distance measurement and the column density measurements also have some bit of errors. And yeah, it's quite high, as you can see, but the error bars are also large. So
Okay.
you can see the lower points are
Right.
So that's the reason why we are proposing for Arcus and also CRISM. CRISM will, when CRISM goes up, and then when I give the next talk, maybe sometime next year, you'll see like narrow bars.
Won't go to 10 to the 48.
Okay, it won't go. So is it like entrained UFOs? Could be. So it could be like some UFOs impinging on the one in the outskirts of the galaxies and creating worm absorbers. It could be. I mean, these are all hypotheses, and they have people have found that the soft X-ray UFOs along with the hard X-ray. So you have UFOs and soft X-ray UFOs in the same spectrum, and that is very interesting. So these are all opening up in the last few years, and these are fantastic discoveries. So the summary is that, yes, ionized outflows are powerful mechanisms, and they have sufficient momentum and energy to displace gas, and these are radiatively driven by AGN, but maybe the MHD and other mechanisms are also at play. But we definitely need the future missions, and PRISM results will come soon. So stay tuned. Now, to give you a glimpse of how it will be, this is Athena, for example. This is a simulation. This is not the real data. The Athena would be enormous improvement compared to XMM. Even PRISM would be enormous. So all of these absorption lines that you see you can actually resolve, and you can measure their intensities, and you can actually get you can estimate the kinetic and other luminosities. And for Arcus, you can see that there's an order of magnitude improvement in comparison to XMM or Chandra readings in terms of the figure of merit, which is a relation between the resolution and the effective area. So these missions will definitely change the game. Now let's move a little bit away from the black holes. Away means kiloparsec scales. And this is also comparatively new detections, because these are ALMA detections. ALMA came up in, I guess, in 2015. And huge amount of molecular outflows have been found in several galaxies. And the interesting fact is that, and these are like carbon monoxide transitions. And interesting fact is that these molecular outflows, if you calculate the rate of the mass outflow rate and the AGN luminosity, they have a strong correlation between the different types of AGN. I'm sorry, I didn't, okay, so this is the L AGN by L bolometric luminosity. And if you have the AGN pumping the molecular outflows at the kiloparsec scales, it means that AGN is somehow talking to the host galaxy at kiloparsec scales. And these are an example of how these outflows work. From my work, we have seen that same results in a sample of 50 AGN, that the molecular outflow velocity and the central AGN luminosities have correlations, and similar correlations that we find. And these all point towards, now this is a nice result in the sense that Fiore et al. Has combined all of these outflows that I've been talking throughout, molecular and ionized outflows, and they have correlated with the airborne, and they have found correlations between the AGN luminosity and the mass outflow rates for different types of outflows. So all in all, AGN talks to the host galaxies, and the mass outflow rates, the kinetic luminosity, all points to the fact that yes, feedback is real, but we still need to quantify and characterize the types of feedback. One last thing I'd like to mention, that how do the feedback interact with the host galaxy? Is it momentum conserving or energy conserving? Still debated. Many papers have been written on this, and one of them have found that it's possibly energy conserving, because they have found some relations here. The outflow velocity. This is the UFO, and this is high velocity, you can see, and these are like molecular outflows. So molecular outflows are sitting here, UFOs are sitting here, and for these sources, they have found that the UFOs are probably impinging on the host galaxy gas and conserving in an energy conserving way, creating the molecular outflows. So these are some of the observational evidences of feedback of how the black hole is throwing matter out and talking in a language the galaxy understands. Now, galaxy also must feed in order to have a feedback. Now, how does it feed? That's a big problem, and how parsec scales or distant matter falls into the black hole and loses angular momentum, feeds the black hole is a big question, definitely. And I'll show you some observational evidence about how this feeding happens. So this is typical spiral galaxy, and I mean, these stars will eventually have some probability to get into accretion disk and feed the black hole. And what are these clouds and how do we detect these clouds in terms of feeding? So again, ALMA. ALMA is the radio telescope. I mean, I should say it's a submillimeter telescope, which detects at a very high spatial resolution the cold neutral molecular gas. And it has done fabulous work in detecting like parsec scales in the sources nearby, parsec scale gas around the AGN. So for example, with NGC 613, this is NGC 1326, you can actually see the gas around the supermassive black holes, and different colors indicate the rotational speed, and there's a PV plot with the position velocity diagrams. But overall, there is a huge amount of movement going on and around the black hole. But the black hole is tiny. So if something is happening at kiloparsec scales, why do we care? So we have to again go back to absorption spectroscopy and see if we get some evidence of clouds there. So there has been studies by, for example, Marco et al. And other people about about changing column densities along the line of sight. So there are changes in the column densities along the line of sight, which means, and it's just days, you see. So in a few days, you see things coming along the line of sight that I showed in the absorption there as well. So these are clouds possibly feeding the black holes because they're very nearby. And in one of the larger studies that I have done, I have found in a big sample of sources, almost hundreds of observations from different sources and different instruments. I've seen that this type of variability, so this is the continuum, and this is eaten up by the gas. So this eating up is the absorption, and this is variable at different time scales, days to months to years. The spectral turnover is a measure of the obscuration, and we indeed see these things. So we are proceeding to the next stage to understand how these gases are clumpy. So torus is clumpy and dynamic, and we have to understand how it feeds the black hole. So this is an ongoing project, and we are still trying to understand what's going on. The last part of my talk is on a very fantastic changing look AGN, which has been big news recently because we haven't seen this before. So what happened is in December 2017.
Yeah.
Okay. In December 2017, a very quiet, docile, nicely behaved AGN suddenly became super luminous. Factor of almost 100 or like 80 in UV and optical luminosity, suddenly, like in a matter of few days. And then it started to decay. When it started to decay, the broad emission lines, which were not there, we thought that AGN is normal in the sense that it is a type 2 AGN, and type 2 means we are seeing, it's a true type 2 because we are seeing directly the black hole and the accretion disk, but we are not seeing any broad line region. So we think that it's neither obscure, but type 2, but it's fine because it is not a great AGN to talk about. Suddenly the thing became very bright. The broad emission line started appearing. So the broad emission line was not there at all, and it started appearing. It appeared and it stayed for a few hundred days and it decayed. And in the meantime, what happened was the X-rays, which is coming from the corona, it jumped up a little and then it vanished at some point and then came up with a bang, and then it died down. Now, initial results showed people thought that it's a TD. So what we did on behalf of like Swift, we continued monitoring this source.
You might want to let people know what a TD is.
Okay, TD, sorry. So TD is a tidal disruption event, and when a star is like shredded apart, alive, eaten up like a black hole alive, if the star is living. So, so and for TDs, there are like theoretical predictions of how it should behave. I mean, there has been quite a lot of theories, which says that it should decay in a manner like t minus 5/3, which should have a slope, nice slope.
But
What-
also tidal streams that can come back and intersect.
Come back, it can be intermittent, it can be repetitive. Yes, it can be. So there are theories, and it's very hard to rule out a TDE. That's because there are so many aspects of TDEs. But what we found over a period of like say 3 years, 2018, 2019, 2020, 2021, which is we are continuing to monitor this source. And what we found that this UV is coming down, has come down to its pre-flare value. Unfortunately, we have someone taken this XMM observation in 2011 when the source was doing nothing. So we have a pre-flare value. So the UV is coming down at a very shallow rate, I mean, shallower than standard TDEs. And the X-rays were there and they vanished. These triangles means they vanished, and they came up with a bang, and then they returned to the original position. While the X-rays were vanished, the radio, we have sparse radio observations. The radio was at its minimum, and this was never before, and we have never seen such things because in most TVs we see that the UV actually followed by the X-rays, and in radio I don't remember if there has been radio observations of TVs, but this is very unique because we see that the radio, this is a pre-flare value in normal times. The dip was there almost by factor 4, and it's coming up. And this is a X-ray view of this. So this is nicer telescope, X-ray telescope, and you see that it completely vanished at some point, the X-rays, and it came back. It stayed on for many, many months, almost a year, and then it came back to normal, and then again it was going up. So
That's a question. On the nicer curve at the top, is that real variability? Are those,
yeah.
the error bars on those points are really tiny? Is that's huge variability.
Huge variability.
Because on the right-hand side, it's very tightly,
Tightly,
very well
yes.
behaved.
So while it was going up, it had a huge amount of variability, and it was random. I mean, it was. I shouldn't use the word, but it was crazy.
Well,
So
you said stars were alive before, so anything.
so exactly. So it's still like this is an open question. I mean, you all are like experts in black holes, but I mean, we still don't understand what's going on, and huge variability, even day scale, like our scales variability were like, I mean, awesome. So
That must set a size scale.
give a size scale, yes, and the size scale is like 10 RG or less than 10 RG, and it's kind of like where a corona should be.
And then it all went away at the.
Yeah, this variability all went away, and then it became so nicely correlated and nicely tightly backed here, and then it fell down, and that is very strange. We still don't understand what's happening, and if you see the optical light curve on that similar time scales by TESS. TESS is an optical telescope. It's actually a habitable world telescope searching for exoplanets. But it also has like all sky capacity, so it took this light curve. If you see the flux, it goes down, optical flux, but within that, it shows a huge amount of optical variability. So this source is unique. I mean, it's highly variable source, even during the time of when it's flaring up, it's going down. So there has been a theory by Sepai et al., Michel Begelman, and we think that this could be a magnetic polarity inversion in the sense that in a matte disk, if there is a magnetic field, so corona is actually we believe corona is possibly a byproduct of the magnetic fields that are created in the accretion disk, and it's sustained by the magnetic fields. If the magnetic fields vanish, the corona vanishes. So what we see in the observations is that the advection, the accretion rate increases, so advecting opposite polarity, and when the opposite polarity cancels the existing polarity, you have a very low magnetic field which helps to vanish the corona. But the accretion rate is still high. The opposite polarity then advects a lot more, and then you get a final magnetic field, which is the opposite of the polarity, but now the same strength. So and then it goes down to normalcy. So this is something which has been hypothesized, and we think that this could be a scenario where this interesting source could be explained. TD is also a suggestion, but it's very hard to explain why the radio is going down. So I should remind you that radio is corona also emits in radio, AGN corona.
So what's happening in the upper left, I see, okay, there's a nice north-south relationship, and then in the second one, there's a north-south and then a south.
So the opposite polarity getting, now the question is how the opposite polarity is formed and advecting, we don't understand. But there may be in some situation that the opposite polarity is formed at the outer accretion disk, and it takes time to get into the inner accretion disk. And when it advects, accretes, and the matte disk, the polarity, the magnetic fields cancel, and then the opposite polarity takes over after some point of time when the corona again reveals itself. So during this time, there is no corona. During this time, there is a corona, weak corona, no corona, again a corona, and then it comes back to normalcy. So this is a theory which Michel Beckerman and Nicolas Sepai has helped us with. And this is something as a graph, like if you consider the accretion rate and the magnetic field as like two different quantities, and if there is an accretion rate of flare, and if the magnetic field goes down, then the expected extra flux for no inversion is something which it should follow. The UV flux and the extra flux should follow. And for inversion, what happens is that the UV flux goes up, and the opposite magnetic field comes in, and there is a dip in the X-rays where there is no corona, and then it goes up again because the accretion rate is still high that we have seen from our figure, and then everything goes down after some time, and the time scales are kind of agreeing with what we see. So this theory is still being developed, and we need more handles.
Are all these AGN, they have like low spin black holes? Or is there a jet possibly?
I'll come to that. So low spin, we don't know the spin of the black hole because interestingly, this is perhaps a very rare AGN where we don't see any iron line. I mean, most AGN, there is an iron line, and the broadened iron line gives you the spin. But this is a very interesting AGN. Even at the highest X-ray state, we don't see any iron line. I mean, I was like, after like 10 years of work on AGN, when I don't see an iron line in an AGN, it's like a book without any pages, something like that. So it's really a mystery. I mean, and this is a sample of TDs. Like as you can see that people have really like these are recent work and fabulous works done on TDs, and this is like these are how the TDs mostly behave. Tidal disruption even behaves, and they mostly come down at like 200-300 days. But ours is like 1200 days. So great. So the thing is, so now something weird is happening. So to answer your question, this is in preparation. In last 1 year, what we have seen is that the soft X-rays has gone up. UV is doing nothing. And we see a flare, exponential flare in the radio. And with VLV imaging, we can see a jet is coming. So this is perhaps the first time we are seeing a jet being formed in a post-changing Lagrangian. And we are going to, like my colleagues at UMBC, Ellen Mayer is going to publish the paper soon, and we will again follow up with the X-rays. But we still don't understand. You see that the corona is doing nothing. The hard X-rays doing nothing. The UV, the main accretion energy, is doing nothing. The soft X-rays, which we don't understand where it's coming from, is going up, and it's now 6 times almost from the pre-flare value. And it's gradual going up. It's not exponential. So here it's almost exponential in the radio.
And do you have an example of how it looks at VLBI scales? Is it just a like point source effectively, just increasing brightness, or there is some structural changes?
Very good point. So what we see is the point source, the core radius, which is less than parsec. This is from the core. But the structural changes are also happening. We see an asymmetric extension. And it is time because like December 2017 has been like 6 years back. So 6-7 years, if the jet started off, then we can expect to see now. Fingers crossed. And this is no correlation. So nothing to expect here. So the power law does not, the corona does not talk to the disk does not talk to the soft X-rays, the soft X-rays does not talk to, nobody talks to nothing. So everybody is doing their own fine thing. And that is the strange thing that is happening now. And we are still trying to understand, and I'll be very happy if someone wants to talk, and I'll be more than happy.
Do you have any polarimetric VLBI?
Yes. The problem, I guess, there has been polarization changes that we have, but I need to confirm the results and get back to you, because the VLBI polarimetric, it's not a very bright source. So the polarimetric results are not very robust, but we see some changes. So EVN is looking at this, and prior to the jet being formed, and now there has been some change, but we have to see if it's not within the errors. So it's
Right, so I'm just thinking, you're thinking about a polarity change.
exactly.
So
I mean, polarimetric change in the sense that if there is a jet, we should see some change.
And did you make multi-frequency VLBI observations? Because like from this extremely steep rise of the flare, I think
Absolutely.
it's like very
If
reasonable to
you want to
compare
talk to
times.
me, I can show you the slides, but it's not
Oh.
published. So I'll be more than glad to show it to you. So yeah, we are seeing those steep rises. Yes.
When you say that, that there's nothing to explain because there's no correlations, so that's what you expect, that these guys aren't
No,
talking to each other?
no. We don't expect this at
Well,
all.
then there is something to explain.
Oh, there, you got me. So the thing is, you really got me. The thing is, this UV flux is something which is putting in the energy from the gravitational bound system. So it's the UV is something coming from the disk. And this is the energy that is main energy source, which is pumping all of the events that are happening, even the corona. And what we should expect, if there is an energy pumping in the soft X-rays or the hard X-rays or in the jet, there should be some amount of energy rise or pump in the UV. Less than 30% of the variations. So it doesn't make sense. I mean, where is the energy coming from? So we have to rethink about the structure of an AGN, maybe. Like maybe the inner disk is soft X-rays, which is pumping in energy, and the soft X-rays is something which is pumping in a jet. And
can I ask a question about that? The other potential energy source here is a spinning black hole.
yes,
Is there a way that somehow the accretion has changed and
that's
magnetic fields are beginning to thread the black hole, and you're having this emergence of a jet?
yeah.
And it's the jet that is causing the X-rays. and
Soft
the radio
X-rays,
flare.
very good point. Very good point. But the problem is that how do we know the spin of a black hole? That's where we are stuck. We could have done that if we had an iron line which is broadened, or we could have done with some other indirect evidence of the spin. But that is where we are stuck. but I'll be glad to talk to you more about like ideas on how to go about it, because this is something which is not explained in standard understanding, and that's the reason why I thought there's nothing to explain, because we don't understand things, so no explanations. So the open questions. So the UV, sorry, accretion. Okay, sometime one C is missing. If the UV accretion disk is not pumping in energy, then how is the soft extra wave getting energy? That's a good first question. Can we recommend, Stanley, comment on the jet formation theory following this unique event? Can we say something about how the jets form? And what is the role of corona in all this? Because corona is the extra emitting blob of plasma just sitting right there, and sometimes it's doing funny things and sometimes it's not doing anything, and there's nothing in between. That's a big problem. And can we constrain the magnetic field strength or its alignment from these behaviors? That's a big question that I want to ask, because in AGN, in supermassive black holes, we still do not have a handle on the magnetic fields threading the disk, and how these are the value of the field, magnetic field, or the orientation or anything. So we still don't understand how these things are. So from theoretical point of view, I'll be very, very, very eager to hear from you if we can help with some observations to pinpoint these things. So that's all about my talk. I'll just end with a slide from a verse from Gita, which is a philosophical text from India. It says, since we are all black hole astrophysicists and we deal with time and space and everything, so it's like, never was there a time I did not exist, nor these rulers of men, nor you, nor shall these cease to be thereafter. So I interpreted it this way, that it's creation and destruction happens only when there is a unidirectional flow in time, and in this universe we may be living in pockets where time flows, and maybe there are places where time doesn't flow. And maybe, so this brings me to the point that there was a steady state universe theory by Fred Hoyle and Jan Narliker. And if anyone is interested to talk to me, and if anyone is working on this, I would be glad to hear. And the flow of time is relative and everything. So this is an open invitation to discuss something beyond what we understand and think. This is my next slide. Of course, I'm the Swift back mission support scientist, and so any questions on Swift mission by NASA directed to me. So I'm also the Swift scientific community outreach lead, and I'm happy to answer questions on Swift, and happy to have ideas of Swift observations and everything that you can think about with Swift. And we have recently written this interesting pipeline, which if you want hard X-ray data in that energy range, and you're unable to like find the data or do anything with the data, and of course the pipeline is hard, so you can't do anything. So you'll need our help. So that's how it's designed, that you need our help. And you can just get back to me. So this is a paper published last year, and we'll be very, very, very happy to help you with anything that you need. And this is particularly important because when you're talking of hard X-rays, there is not any other telescope which can have a focusing in these energy ranges, because BAT is a 1/6 field of view operating instrument. So 1/6 of the sky it is seeing at every point of time, and it's just doing that every time. I mean, all the time. So if you have a source, your choicest source, or if you don't have a choicest source, you can just come to us. We can make a choice, and yeah, and we can work out, because we can actually single out the source from that particular field of view, and we can track the source, how it evolves in this. And this pipeline is important because that data has not been extensively used by anyone, and we are trying to have it on HISARC and other websites so that people can actually get a glimpse of this. Thank you for your attention.
Thank you for a very interesting talk. We have time for a couple of questions, maybe.
Yeah, thank you for the talk. I'll definitely have some topics to chat with you after that. But now I have a short question on the first part of your talk, when you like with a nice diagram of all these outflows, different velocities, and how you like typically probe them with absorption. But these are the same regions we see in like broad emission line, narrow emission line, right? So I mean, the line width doesn't depend if it's absorption or emission, it should be the same. So how does it relate, like if we probe the same source with emission and with absorption, do we see like consistent results on velocities?
Yeah, so if I've got your question correctly, how do you know if they're the same systems or the same similar, like, of course that they are different systems because they have different ionization parameters, they have different outflow velocities, they're located at different distances from the supermassive black holes. And that's what is the summary slide that I have presented here. Is this. We definitely have different, so these are from extensive sample studies from different sources. And for even a given source, it's rare but not uncommon. I mean, you can see all of these four. And all of these four are there, and there are different distances, of course, because you cannot have a narrow absorption line with so low ionization parameter sitting right next to the black hole, because it will be all ionized. So these distance scales that we have estimated are mostly from indirect means, like either the velocity or the ionization parameter. You cannot sit right there and stay neutral.
I mean, like, does the results agree if you study them in absorption as you typically do, and with emission? Because when we see narrow emission line, broad emission line, do the results agree between emission and absorption lines?
I didn't get your question. Like emission and absorption are two different aspects. So
Yeah.
emission line, you don't see much of you see emission lines, but they're not spatially resolved. You see just a blob there.
Yeah, but I mean the velocity spreads, they should be the same. The width of the lines, they should be the same whether it's emission or absorption.
Yes, width of the lines are sometimes same. There are narrow emission lines, broad emission lines. So the broad lines actually are good tools to measure the black hole mass because you assume the real velocity.
Yeah.
So yeah, so the widths are sometimes the same, but not always.
So in the general picture that like you draw and interpret here is that there is basically a smooth transition from like the extremely relativistic jet in the middle, then there is a slower but still reasonably fast outflow.
This is a hope.
Yeah,
we
and
hope
then like
that
it slowly.
We have a smooth transition.
Yeah, and then it smoothly becomes slower and slower.
Exactly. And that is something obvious because you're not pumping in energy. So as you go out, you become slow.
So the final part, you're changing lookage here. You say that it's a mystery, but to me, it kind of looked reasonable. And I'm just thinking in terms of X-ray binaries. You know, they go through these transitions from hard to soft state. So the picture is when it's in the hard state, you don't have a disk at inner radii. The disk is limited to outer radii, okay? And then at some point, the system decides to make a transition. What happens is that then the disk comes in. During that transition, it sends out a jet. There's a so-called jet line. When you cross the jet line, bang, a jet comes out.
Okay.
And then it becomes a soft state system where the disk is now all the way down to the black hole.
Sure.
I think your guy did the same thing. I had a disk at larger radii, no disk at small radius.
Okay.
So that was producing my UV.
Yeah.
And you made some hard X-rays from the inner region,
Corona.
and ADAS, corona, whatever you want to call it. Then your system has come in. When it came in, it crossed the jet line and produced your ejection, which is producing your developing jet, still coming out. And then when the disk reached the black hole, you've got your soft X-rays. That's the inner region of the disk. So I'm imagining that your disk consists of soft X-rays from the interior,
Could be
UV from further out. The UV was always there. The soft X-rays came during the transition. I think it sort of qualitatively fits mostly everything you're showing.
Yeah. So thank you. And the thing is, like, the corona is something which is also like bothering us because the hard X-rays that, like, you're talking of soft X-rays in the inner disk.
Yeah.
The corona is something which we think of something like a really inner disk or like something above the disk. So it's also doing nothing. I mean, it's we think corona is the base of a jet or something, something which helps in creating the jet. So corona is doing nothing, like hard X-rays, no variations, little variations, mostly like the soft actually went up very, very smoothly. Yeah, it kind of like fits in that scenario because the soft X-rays are moving up and then the energy is enough and then you shoot out a jet and then you have an exponential rise
Right.
and then you see.
So the part that's bugging you is why there are hard X-rays
Yeah,
before all this. But it's a hot accretion flow.
okay,
I would have said, what's the big deal? There's an ADAF there, it produces hard X-rays.
okay.
Yeah. We should talk.
Yeah, sure.
But my understanding of the X-ray binary phase transition shift is that there's your higher spinning systems, right? And the jet is launched because of the
Well, there
spin.
is some spin. Doesn't have to be necessarily high spin. We don't know what
Yeah,
the spin
but
of this
it
guy
is,
is.
but it's because of the spin that the jet's launched.
Certainly,
Is that a fair
yeah.
statement?
Yeah, I think that's a fair
So
statement.
here, would you say that this black hole does have to have
Yeah, yeah.
significant
Okay.
spin?
Yeah. Jets come from spinning black holes, yes. But it doesn't mean 0.998. It could be 0.5 or 0.7, but it's not zero. I agree with you.
Okay.
So I
So
want to
we-
make sure I understood. So
Yeah.
So we have to try and see if we can get a spin measurement of this black hole, but it's very hard, but we will definitely check in some way. Because there is a, as you mentioned, so there is a model in AGN by Chris Dunn, which is the soft X-rays are coming from the inner accretion disk, and it also measures the spin of the black hole. So indirectly, the soft X-rays are a result of like a spin, accretion, everything. So if we fit that model, then we can indirectly get a spin of the black hole. And thanks for these points. So I'll check if we can do that, and then we can say that if the spin is there, and so it supports the claim, right? Okay, great. Thank you.
All right, I think we thank our speaker again. Thank you.
But Fabio, I think we also have to fix the screen.
Why was
Yeah.
it flickering?
Yeah.
It's always been like this, I think.
But I think every time.
Yeah, but that's not why it has to be that way in the future.